Turning now specifically to dissolving ionic compounds in water. Here's the general expression for it: solid ionic compound going to the aqueous, cation and anions separated from each other. Okay, ionic forces in the solid, ion dipole interactions associated with the cation and the anion. Now, for simplicity's sake, I'm just talking about a 1 plus cation, 1 plus minus anion, but of course the idea is going to go for any particular ionic compound. Now, in order to think about the energy associated with that process, the delta H of the solution, we're going to take a little thermodynamics trick and break it up a bit. So instead of going straight from the solid to the aqueous ions, let's think about going from the solid to the gaseous ions, and then from the gaseous ions to the aqueous ions. Okay, so of course, as you hope you remember from all of our thermochemistry and thermodynamics discussions, we add together these two equations, we get the overall equation. So when we add together the delta H's for these processes, we'll get that overall delta H. Now, this first equation is actually familiar to you, or it should be familiar to you, because it's the reverse of the lattice energy. Lattice energy is when you take the gaseous ions, bring them together to make the solid ionic compound. Here we got the solid ionic compound go to the gaseous ions, so the energy of that is the minus the lattice energy going that way, so minus the lattice energy going the way we're looking at. Now, this one here is one you might not have seen before. The gaseous ions going to the aqueous ions. Have to be very careful how I say all that. Well, that's called the heat of hydration. Okay, if it wasn't water as the solvent, it would be the heat of solvation. As water is the solvent, nice special one, heat of hydration. So add together these two equations, we get the solution, the dissolution, the dissociation equation, however you want to say it. So add together these two energies and we would get the heat of solution. So the heat of solution for an ionic compound in water is minus the lattice energy plus the heat of hydration. Okay, and if we think about what we're saying before, if this is, of course, lattice energy is a negative number, so this is a big positive number. If this is more positive, significantly more positive, then this is negative, and these are always negative. Well, then it's going to be an endothermic heat of solution, and if it's too endothermic, it's not going to happen. Conversely, of course, if the whole lattice energy bit, this positive bit, is smaller than the negative bit, delta H of the solution would be negative. Combine that with the nice positive delta S, and you would have a negative delta G. The solution would happen. The ionic compound is soluble. Now, it is worth again talking a teeny bit about not just really lattice energy, because we've talked about that before in the thermochemistry module, but the heat of hydration. Both of them have the same trends. Both of them increase as the charge increases, which makes sense. If you've got a 2 plus cation versus a 1 plus cation, the 2 plus is going to hold on more strongly than the 1 plus. So you have a bigger lattice energy and you have a bigger heat of hydration. Now, in both cases, because lattice energy and heats of hydration are exothermic, when I say bigger, I mean more exothermic. And in both cases, as the size goes down, the energy increases as well. Okay, so in other words, the size and either the lattice energy or the size and the heat of hydration are inversely related to each other. The bigger the ion, the more spread out is the charge, so the smaller the charge density, so the less it is going to hang on to whatever it's hanging on to whatever it's attracted to. Now, you can see this from just some values of heats of hydration. So if we look here, for example, at 1 plus cations, you can see these are the values here. 2 plus, much bigger. And then as we get bigger ions, lithium's the smallest ion, then sodium, then potassium, you can see that the heat of hydration gets smaller. Same thing for the alkali metals. Magnesium is a smaller cation than calcium, so magnesium has the higher heat of hydration. So as charge goes up, heat of hydration goes up. As size goes up, heat of hydration goes down, or as size goes down, heat of hydration goes up, however you want to think about it. Let's see if I can't present the whole concept to you visually. Let's plot energy going up. We start off with the solid ionic compound, energy down there. We then break it apart into the gaseous ions, and of course the energy needed to go from the solid to the gaseous ions is minus the lattice energy. Now we've got our gaseous ions, we're now going to put them into water, so we're going to solvate them or hydrate them, and of course that's an exothermic process because we're making those interparticle forces. We're making the ion dipole forces. So therefore we're going to have the heat of hydration going in, which is an exothermic one, to take us down to the aqueous ions down there. Okay, now 3 possibilities. The first possibility is we put the heat of hydration in. You see it's exothermic, so go down and then goes down further than the original solid was. In other words, the heat of solution is negative. Going from there to there, that is a negative heat of solution. Okay, now in that case we've already said if the heat of solution is negative, if the heat of solution is exothermic, put that together with the positive delta S and things will be soluble. I'm going to call that situation 1. Situation 1 is when the heat of solution is exothermic. Second possibility is that the heat of hydration is not quite enough to get down to the original solid. So in other words, the heat of hydration is not quite enough to overcome that lattice energy that you need. Now in this case here, delta H of solution is greater than 0, but it's still a small number, so it's quite not nice, quite as nasty as the delta S term is nice. So this would still be soluble, a slightly endothermic heat of solution. Call that situation 2. Finally, of course, the heat of hydration might be quite a bit less than the whole lattice energy. So we're up here, so therefore the heat of solution going from there to there is not just positive, it's very positive. So therefore the heat of solution much greater than 0. That's an insoluble situation. In other words, the ionic compound is not going to dissolve, and we'll call that scenario number 3. Now with that in mind, let's look at 6 ionic compounds. 3 pairs, 1 soluble, 1 insoluble. Start off with some fluorides. Sodium fluoride is soluble, calcium fluoride is insoluble. Sodium fluoride, the heat of hydration, sodium is minus 406, that was on that table on the last slide. Fluoride minus 505, put it together, minus 911. The lattice energy of sodium fluoride is 923. So in other words, this is 923, this is 911. So there's a difference of plus 12. Well, we said we can handle a relatively small endothermic heat of solution. Conversely, calcium fluoride we know is insoluble. Well, calcium's heat of hydration minus 1577. We got 2 fluorides, that's 2 times the minus 505 that's fluoride. So that's minus 2587. Lattice energy is 2630. So this is 2630, this is 2587. There's a difference of plus 43, which of course is obviously too big because we know calcium fluoride is insoluble. Let's look at another pair. Both of those, by the way, represented scenario number 2 for sodium fluoride, calcium fluoride scenario number 3. Let's look at sodium chloride that we know is soluble and silver chloride that we know is insoluble. Sodium minus 506, chloride is minus 363, there it is, minus 363, but silver minus 475. So sodium chloride minus 769, silver chloride minus 838. Lattice energies for sodium chloride 786, all of these are in kilojoules per mole of course, and silver chloride 915. So putting those together, sodium chloride is plus 17. Well, that's scenario number 2, still a endothermic delta H, but small enough that its sodium chloride is soluble, but silver chloride we know is insoluble, scenario number 3, because it's got a plus 77 kilojoules per mole heat of solution. 45, 77, too big for the entropy to overcome them. 12 and 17, given that sodium fluoride and sodium chloride are soluble, obviously the entropy, the nice entropy, is enough to overcome this bad delta H. Final pair, sodium hydroxide and magnesium hydroxide. Sodium hydroxide, well, sodium minus 406 again, hydroxide minus 519, magnesium minus 1921, hydroxide minus 519. Put them together, you see the numbers. In this case, sodium hydroxide is actually an exothermic heat of solution. It's quite exothermic. If you dissolve sodium hydroxide up to make concentrated sodium hydroxide solution, you do notice a significant increase in heat. So that's scenario number 1. Magnesium hydroxide, though, plus 47 is sufficiently endothermic that magnesium hydroxide is insoluble. Scenario number 3. So hopefully, I tried to take a very big topic and distill it down to 16 minutes. You now have a better understanding of the energetics associated with solubility, with making solutions, as to how you can explain with thermodynamics why some things don't dissolve and other things do dissolve.